right? So we're going to go over three major things: the gravity floor framing system, the lateral system, and the foundation design. So this is the introduction. So why did we choose this place? So first of all, existing there right now is the Trump Tower, and it's also right next to the Central Park, so it's a great tourist attraction. For most of it, obviously. It took about 15 to 20% of our material costs. And concrete provides compressive strength and stability. We chose the I shape because of its efficient material distribution and it minimizes costs. Its resistance to bending, shear, and various load effectively. And it's adaptable to complex architectural designs.
So next we'll talk about our gravity floor framing system. Once again, on the top is the shear load, the shear diagrams, and on the bottom is the movement diagrams. So for our beam analysis, we chose to do a centralized beam, which was a W16 by 31. It composed of 36 studs and has a camber of 1.5 inches. So for our live load analysis, on the left side of the screen, this is the information that ETAPS provided.
So for our lateral system, we did use concrete shear walls as well as lateral bracing. The effectiveness of concrete shear walls is influenced by the thickness, which varies based on floors. This is cost effective while meeting structural requirements, and it's also an efficient design for load distribution. The effectiveness of lateral bracing minimizes lateral displacement and drift, and it increases overall structural stiffness, and it also offers a cost-effective solution for stability and safety. So we did, for floors 1 through 20, we used a 28-inch wall and 9,000 PSI strength concrete. For floors 21 through 32, it's a 24-inch wall with a strength of 9,000 PSI. And for floors 33 through 40, it's a 20-inch wall and a strength of 6,000 PSI, as well as lateral bracing on floors 20 to 21, and that size is W24 by 94. We did make the thickest walls with the highest strength on the bottom because it will have higher loads. So this is the displacement for diaphragm. Our allowable displacement is H over 400, which is 600 feet times 12 inches per foot divided by 400, which gave us 18 inches. So our first design, we had just a 12-inch wall thickness with 4,000 PSI. And it gave us a really high displacement of 64.1 inches. So we did have to reconsider our design, and we ended up changing the concrete wall thickness as well as the strengths. And that gave us the 18.5-inch displacement, which was right over our allowable of 18. So we did add lateral bracing on floors 20 to 21, and that got us to 16.8 inches of displacement. So you can see that in our graph here, the allowable is the dashed line, and the 16.8 is just right under.
So to go over the foundation design, this is our dead load plus live load soil pressure deflection diagram. And as you can see, with the 0.75 factored in, as well as the wind load, they look practically identical. This is a 3D. So as you can see, all the pressure, the soil pressure, lies where the core is. And basically, that foundation distributes the building's weight evenly over a large area, and it provides stability against structural loads, including wind loads, seismic loads, and gravity loads. The soil bearing capacity we used was 20 KSF. The material was 6,000 PSI. We used a 96-inch slab depth, and that's pretty much it. So here's the shear stress, 11.044 inches squared per foot. At the coordinates, again, you could probably see where it is. And in the bottom, the maximum moment was 29.6794 inches squared per foot. And Yeah, so we essentially got these by putting design strips on the X and Y coordinates. That was the conclusion. So here's the material takeoff. So as I was saying before, the steel cost typically ranges from 15 to 20% of the total project. And you can see here, we used A992FY, which is a steel type material, for the column beam and brace. So we took all the weights in kit and we added them together to get 5,186.2 under the steel kit. And we divided that by 2 in order to get in tons. And then for concrete, we had for walls in 9,000 PSI and 6,000 PSI, as well as the floor in 4,000 PSI, and we added those together once again to get 59,691.6 gibbs. And if you're wondering what the 150 is, that's just the self-weight of concrete. So in order to convert it to feet per cube, there's a lot of confusion for the foundation. We got through it. And there's no challenge without lessons learned, right? So every challenge we had was a lesson learned. But I think the biggest challenge that we can all agree on is that we didn't have enough time to learn Rhino and Grasshopper and E-tabs. And also,
Yeah, we'll be out of here by 2.
it increases every hour.
Yeah, so we're gonna finish